to Zeke's talk. It's looked like a really exciting one this month. Rapid home energy assessment through vehicle-mounted thermal imaging. Zeke's the head of energy science and analytics at Essess. Before that, he was chief scientist at C3, which is now C3 IoT, and the co-founder and chief scientist of Efficiency 2.0. He's also a research scientist at a non-profit think tank called Berkeley Earth. And I clarified earlier, that is an evenings and weekend thing in addition to a full-time job. Kudos to you. And before that, a PhD at Berkeley Energy and Resources Group. Should be a good one. Zeke, all yours.
Sure, thanks. I'm actually finishing a PhD at Energy and Resources Group. Also a
Good one.
evening and weekend thing. So I'm Zeke Hausfather, and I'm going to tell you a little bit about what we're up to at Essess. I want to make sure that this is not framed as a company pitch. I'd rather want to talk to you about the cool stuff under the hood, the data analytics. As I'm going, if you have any questions, feel free to raise your hands. I'm happy to take interruptions. So as a quick background, what Essess does is vehicle-mounted thermal imaging. The company started out of MIT in 2010, and I came on board in 2014 to sort of head up the energy analytics team. We have vehicles. They look like this. They have a thermal imaging system mounted on top of them that contains both near-infrared and far-infrared cameras. So near-infrared gives you essentially black and white night vision type image, and far-infrared gives you the actual heat signatures. They're both useful, as we'll get into a little bit. We also have a number of LiDAR instruments, a 3D LiDAR on the top, a 2D LiDAR on the front, and various other, temperature, humidity, environmental sensing. And so we drive through neighborhoods at night, about 10 to 15 miles per hour, and take infrared videos as we go, scanning all the homes we pass. We can get, depending on how dense the homes are in an area, somewhere between 5,000 to 10,000 homes per night. We isolate the homes, we figure out how emissive their surfaces are relative to other homes nearby, translate that into an estimate of how much they could save by investing in attic insulation or air sealing or other similar type measures, and partner with utility companies, folks like Duke Energy, PG&E, a number of other folks, as well as we've done work with the military, with insulation installers, contractors, folks like that. And we usually directly run the efficiency programs on their behalf. So we send paper mailers to homes with a thermal image of the home in the mail and some targeted recommendations around what they can do to save money and promoting any rebate or retrofit programs that our utility partners might have. So this talk is going to be in two parts. The first part is going to focus a bit on the computer vision challenges. As a caveat, I am not part of the computer vision team at the company, so I can present it, but I might not be able to answer more technical questions on that front. The second part of the presentation is going to focus on the energy modeling side of things, how we take these thermal images and turn them into targeted and actionable recommendations for homeowners. So here's the rig itself that we use. As I mentioned, it's both near-infrared and far-infrared cameras. We're actually using 4 of each type of camera, and 2 on each side, so we can get a wide range of imaging. With this, we can get up to about 5-story buildings, depending on their offset from the street, which is mostly what we're focused on. And we're collecting a lot of data as we go. So here's what the people driving the car see as they're driving down the street. You have sort of a 3D LiDAR point cloud of the area they're going through, and you have both the far-infrared on the left and near-infrared on the right imaging, the top and the bottom. And so that's sort of the raw data that the vehicle is collecting in real time as it's traveling through communities. We generally have to scan in relatively cold conditions, so below 60 degrees, because we need a heat differential between the inside and the outside of the building in order to figure out the emissivity and figure out how much heat is leaking through the walls, which limits us somewhat. We can't really scan in the summer, even though there is a heat differential between the inside and the outside. The sun shining on the building is going to screw up any type of reading we could reasonably take. So we tend to focus on doing this between October and April or so, depending on what part of the country we're working in. And we collect a lot of data. We collect close to 6 terabytes a night of data per vehicle, which leads us to a fun problem where we don't have the bandwidth, particularly for a mobile vehicle, to send the data directly to the cloud. So we have to store it on the vehicle and then mail. We used to just mail terabyte hard drives or 5 terabyte hard drives. Now we use the AWS Snowball, which is a great solution for folks who are in that particular situation. Collect it all, we send it out when it's full, we process it in the cloud, and then we have our images and our energy analysis to work with. So I'm going to dive a little bit into how we actually do the imaging and the image processing. And the reason why it's important is that we're essentially taking a continuous video as we drive down the street, about 10 images per second or so. And most of those images are not going to be useful. A lot of them will be trees, a lot of them will be in between buildings, a lot of them will be a small portion of the building. So our first challenge is to figure out, okay, how do we get a nice image with the building centered on it? The camera itself is fairly narrow, so often we have to stitch together a bunch of images seamlessly. How do we automate it? So humans don't have to say this is the center of the house, because that sort of thing isn't immensely scalable. We did that in the very early days, but obviously when you're sending, when you're scanning 500,000 or 2 million homes, you can't do any sort of manual processing with that. So this sort of goes through really quick the different steps in the building identification pipeline. So we take GIS data, building footprints if we can get them. Unfortunately, building footprints are not available everywhere in the world, so often we're stuck only with parcels, which have the whole property area. The home is a small bit of that. We also use various other GIS data sources when we can get them. That helps bound the area of interest that we're looking in to figure out where the home is. We do image registration and stitching, so we take both the top and lower image, we have to stitch those together. We also co-layer, as I'll describe in a little bit, the near-infrared and the far-infrared image, so we can get more features and texture out of it. We have to do a facade detection. We're interested in where the front of the home is, that way we can weed out, we can both detect this is a house, this is not a house, and we can also weed out features that are blocking the house, like trees or ground or other things that we don't want to analyze the thermal properties of. Component segmentation, figuring out what's a window, what's a door, what's brick, what's siding. Different materials have very different emissivity properties. So, a brick wall and a siding wall will look very different in an infrared image and will have very different temperatures no matter what their insulation level is. And so being able to normalize for that is really important for the analysis. So having a computer vision approach that can differentiate is important. And then finally, taking those components and processing them and figuring out, are there leaky windowsills? Are there leaky doors? Is the wall poorly insulated? Are there soffit leaks? Is the attic poorly insulated? And turning that into an actual savings potential for that home and a targeted recommendation for the homeowner, as well as a pretty image that we can send them in the mail. So I'll go through stitching really quick. As I said, we take a top image and a bottom image. We have to seamlessly stitch them together. So here's an example from the near-infrared, which is sort of just a black and white image, but it has a lot of features. It's almost like a photograph of the home. Here's the long-wave infrared, which doesn't have nearly as clear features, but has the thermal properties. And so they're both stitched together, and we co-register them. So they're separate images, separate orientations. We have to figure out automatically how to overlay them on top of each other seamlessly and create a combined image. And so here's an example of what that looks like when the vehicle is actually driving by. So this is the co-registered near-infrared and far-infrared image. This isn't exactly the color palette we're going to send people. We tend to enhance the contrast a little bit and the color range a little bit in the final mailers. But this is what it looks like for us internally. Move on to facade detection really quickly. So we use a histogram of dense DAISY descriptors over features in the image in its center region. We also have a support vector machine-based classifier, and we have a huge set of training data. So we had folks, mostly in Pakistan, manually tag about 150,000 homes, draw polygons around the different features in various parts of the country. It gives us a great training data set we can use to help train the system to figure out both what is a home facade, so the overall bounding box of the home, as well as specific components, as I'll describe in a little bit. And sort of here's what that facade detection looks like in practice. So as we're driving down, the red means there's no house centered in the image, and whenever it turns green, there's a home in the image that's useful. So you can see there it is. And now it's green for a second until the tree overlaps too much. There still are occasional false positives, so there has to be some manual QA still in the system, at least when we don't have building footprint GIS layers. But it's pretty good. It's about 98.5% accurate at this point. So then we have to identify the actual facade of the home. We want to remove things like sky and ground that are less relevant to us. So we first use sort of an image recognition approach, which isn't perfect, but can get us a rough sense of where the boundary around the home is. And so here's another quick video showing, as the car goes by, the system detecting the bounding boxes of various buildings. Again, it's not perfect. It'll get trees sometimes, and cars and things like that need to be excluded, but it's a first step in getting the facade of the homes. Now we have this 3D LiDAR data, and the 3D LiDAR data lets us actually figure out the relative spatial positionings of objects that we're driving by. So we can figure out if there's a tree in front of the home, well, it's in front of the home. We can figure out where the actual plane of the home is and exclude things that are in front of that. So here's an example of what the 3D LiDAR will say is objects that are background or foreground. They're not part of the facade. So the image to the right is what the system thinks are non-facade objects. We also extract a ground plane from the 3D LiDAR and the 2D LiDAR. And so as the vehicle is driving, as you can see in this video, it's picking up what is the ground and not part of the home. So the green dots are covering the ground. And we can exclude that from the image as well. So we're not analyzing the thermal properties of the ground in front of the house, which would kind of mess up our overall analysis. And then, there we go.
That's a property of LiDAR that's able to do ground detection.
Yeah, I mean the ground is flat, so we can look for a flat surface extending out from the vehicle that doesn't go up. So it gives us a 3D point cloud, and it's pretty easy to pick out what is flat and what isn't flat. So talk a bit about the facade detection in practice. So all those things go into determining where the actual facade is. So this is the raw image before any processing. Here is the initial facade estimation mask that doesn't have any LiDAR information included in it. Here is the 3D based obstruction mask, so things that are in front of the facade or in the background that are not on the same general plane of the house. Here's when you combine them, you end up with something like this. So, we're taking out the car, we're taking out the bush in front, and ultimately we can overlay, or we can create a polygon with the obstructions removed, and this is ultimately the part of the house that we're interested in analyzing from the thermal image. Well, we also want to figure out where windows and things are, but I'll get to that in a little bit. But this is sort of the base starting point in terms of the facade we're looking at. We also want to figure out what are the individual components of the house. Yeah?
Sorry, why I can see why you have to subtract everything that is obstructing the house.
Yeah.
I can see why that's important, because that affects your denominator, presumably. But why do you care so much about the facade? Because presumably, when you're a thermal image of the sky is presumably very easily subtracted.
The sky is. If there's a tree above the house, depending on how much sun the tree soaked up, how soon after sunset we're scanning, it can get a little bit hard. The sky is easy, but other things in the background can be difficult. Or
if you were to do
if we're looking uphill and there's another home behind it or something.
Oh, okay.
Yeah.
Right. Okay. Fair.
So there are a lot of edge cases that can creep in there. And so then we want to figure out what are the individual components of the home. So we have again, we have a fairly large data set of hundreds of thousands of individual tag components of homes. People manually drawing a box around, this is a window frame, this is a door frame, this is an attic, this is a wall. And we can use that to train the system to be able to detect those and to figure out what the contour lines between them are. And so here's what it looks like when the vehicle is detecting, or the system's detecting contours on homes. So there you can see all the contour lines being drawn as it goes, which is pretty cool.
So the in-car system is doing all of this detection and sort of separation?
No, this is all post-processing in the cloud. Yeah, the in-car system is just collecting the raw data, and we send it all up to AWS and do everything on that. It wouldn't be practical to process it all in the car. It's a lot of CPUs. And then finally, we want to extract the individual polygons. So we have the contours, but we can look for closed contours and try to pull out individual polygons that are different parts of the homes, doors and windows. And so you can see an example here of what the system thinks are the distinct parts of the home that are differentiable. And then finally, the actual detection of specific components, where we have a data set of component tagged homes. We use sequential images to try to refine our estimates. So we're going to take a picture of the same window maybe 10 or 12 times as we're driving by the home from different angles. And we can use all of that in informing the system's guess of what different features are. And the system, of course, improves over time because as we're identifying more and more features, and we're still doing a little bit of manual work too, we can keep adding that to the system and improving the identification. So here's an example, and it's a little bit hard to read these, but there's essentially little boxes around the different components. as well as a probability score for each of them of you know, essentially the system's reliability that that is in fact a window or that's in fact a door. Let me show you what that looks like in a video. Stands out a little better. So as the car drives by, you can see all the different features of the building are detected, and you know, we're not perfect. We're going to miss a window or two here. We might have some false positives, but for most homes, we get most of the features down. You know, here's another image as it goes. And then finally, you know, once we have things like walls or parts of the home, we can also use the temperatures to try to segment them out a little bit. You know, so this is for example, essentially using the range of temperatures on the surface to try to figure out what is the same type of surface. It's important, as I mentioned before, that we figure out what the material type of the surface is because of the different emissivity properties of materials. So we both do that based on the temperature ranges and also on the texture. So the computer vision can look at the different texture patterns of the home and identify the same texture across different material types. So here's a picture of the texture-based region segmentation that the system is doing.
Question?
Yep.
Seems like windows would be relatively easy, but doors may be a little more challenging.
Doors are a little more challenging, especially because there's a lot of different types of doors.
Yeah.
A wooden door,
And there's doors
wooden door
with
behind the
windows.
screen, yeah. I mean, sometimes we'll mischaracterize a door as a window if it has a glass front. What we're focusing on mostly with our programs right now are walls and attics, and to a lesser extent, window frames, but those are a lot harder to do.
Yeah, I mean, that is actually, you know, one of the major sources of energy loss in a home, so I would think that detailed analysis of the windows would be valuable.
It is, and it's an area that we're trying to focus a lot on, particularly if we can use thermal imaging as maybe not quite as accurate, but a quick replacement for something like a blower door test, just to get an initial estimate of what homes have very leaky window sills and door frames. You know, we're not going to be able to capture leaks we're not going to be able to differentiate air leaks from other things in other parts of the home, but for window frames and door frames, if there's a very hot area around them, it's usually attributable to air leakage. Yeah.
I'm very curious about how you identify texture, especially when you're driving by at night, there's no light, no street light, and what exactly is your LiDAR really sensitive?
So it's not the LiDAR primarily for texture, it's the near infrared. So and we actually have a near infrared floodlight on the car. I forgot to mention that on the technology side. So we're shining a near infrared floodlight on all the houses that we're passing, which is invisible to the people in the house. You know, they're not going to see a floodlight on them. We get the police call from us enough. We don't need that. But we shine a floodlight and take fairly high resolution near infrared pictures, which have all the features that, you know, essentially a black and white color picture would have, which gives us texture pretty well. The far infrared isn't nearly as good for texture because it's just heat. And, you know, there are similarities, but it's not that useful.
And just to clarify, so in terms of identifying who can or should save energy, you just need to know total emissivity without needing to classify walls and windows and doors. It's the reason you're going through all of this trouble is that you want to be able to offer more targeted suggestions about how one could save energy.
Not necessarily. So the problem with just using overall emissivity is material type is going to come to bite you a little bit. So the worst insulated vinyl siding house is generally going to be colder than the best insulated brick house in a lot of cases. So the material property has a big impact on the relative emissivity that the vehicle observes. It also has an effect on the amount of residual solar heat that's held, which is one of the main reasons why they're so different. So if you look at a brick wall, it's going to be warm in part because it still has some heat left in it from when the sun was shining. And south-facing and north-facing brick walls are going to be a bit different. For siding, it has very little thermal inertia, so to speak. So knowing the material types and things like that is pretty important for the analysis. I'll get to that actual analysis in a little bit. But what we ultimately want to do is say, we looked at 2,000 south-facing brick walls in this neighborhood in this night. Here's the worst 20% of them in terms of their emissivity, accounting for external temperature and wind speed and various other factors that can mess it up.
Presumably the other way of doing it would be to drive by twice at 2 different times of the day, and that would allow you to subtract out the effect of solar radiation, but it would require you to drive by twice.
You'd also have to have an assumption of what sort of the decay rate of solar heat is from that wall, because it might not be linear. We use, I'll get to this in a little bit, we use a regression approach that in one of the regressors is time since sunset for that particular location, as well as orientation and the combination of those two factors to try to take it out. Yeah?
So just to stack on to the, if you were to drive by twice question. So first of all, is it one drive by per house?
Well, it's generally one drive-by per house. You know, sometimes we end up driving back on the same street, but it's not, we try not to do that if we can avoid it, just to get as many houses as possible.
And have you done any experimentation on, you know, let's say you drive by a house and then drive by 3 hours later, or on a different night,
Yep.
trying to understand the schedule or control system in the house?
So we haven't tried to look at the control systems per se. We have used repeated drive-bys as a way to test the system to make sure that we are correctly addressing things like thermal heat, you know, that we get roughly the same percentile of all the homes in our analysis on a second drive-by that might be 4 hours later. Looking at the control systems is an interesting idea. For a residential home, it might be difficult just from 2 specific drive-bys to figure out that much unless you know what's going on inside the home. But it might be worth thinking about.
Just to tag on to that, like, you know, if you only drive by once, how do you account for behavioral differences and, you know, coincidental vacation taking and all that stuff? Like,
So we don't necessarily. You know, if you're on vacation when you drive by and your heat isn't on, we're probably not going to send you a mailer saying you need to improve your insulation. So we're going to get some false negatives because of that, which is fine. You know, we're not trying to give information to everyone. We're trying to identify, say, the worst 20% performing homes and target them. There's also some issues around thermostat set points that are a big uncertainty. There are differences in thermostat set points between homes, and while we've toyed with potentially trying to figure out based on the overall emissivity of the home if there's a way to pull that out, it's really hard. And very few homes have smart thermostat data available, so we actually know the set points. So we generally have to make a blanket assumption of set points, and that's going to lead to some uncertainty in the analysis.
So I'm really curious, how is the driver aware of whether or not they're going too fast? Is there some kind of feedback mechanism?
So
that says,
there's
"Slow down,"
actually
you know?
there's actually in the look. So the driver has this big iPad. Well, there's 2 people in the car. There's the driver and a co-pilot. The co-pilot is the one who should be looking at the big iPad, not the driver. But the big iPad has all the camera data, and it also is set up to flash an alert if it's going over 15 miles per hour.
Okay. Okay.
Yes?
Do you identify solar panels or obstructions the same way you do trees for attic space? It seems like that would draw the attic space.
So solar panels are a tough one. They're not, in the areas we're scanning, they're not that common, so it hasn't been a huge issue for us. It's something that we could probably train the system to figure out, but we don't have a good enough training data set of homes with solar panels to do that. But right now, in most cases, solar panels are going to be treated as part of the attic because they're so flat to it that it's hard to pick them out. I mean, something like this might get that they have a different texture, but at the moment, we're not specifically looking for them. But it's something that we want to try to do eventually. We have been doing a couple other projects that are not energy efficiency related around detecting utility poles, utility lines, transformers, overheating transformers, things like that. So we've been using some of these computer vision tools to detect other things, but not solar panels so far. So if folks don't have any more questions about the computer vision side of things, I'll move on to the energy modeling side of things.
Actually, one more. So do you formally ensemble all of these models together, or is it some kind of weighted voting system? Like, what's the aggregated output of all the different classification approaches that you're taking?
Well, so each of the models has a somewhat different purpose. You know, one model is to detect what's a door, what's a window. Another model is to detect what's the texture type. So they're all quasi-independent. What we do ensemble is the multiple images of the same home. You know, to figure out if we're taking a number of good images from slightly different angles to make sure that we're not missing anything.
Cool.
Yeah.
One more image question. So did you guys consider photogrammetry, or you hop straight to LiDAR? What that choice?
We hopped straight to LiDAR. To be honest, I don't have the expertise to know the specific reason why, but as far as I know, we've always been using both a 3D and a 2D LiDAR. So energy modeling. So we have all this data, and we have characteristics of the home in terms of windows, doors, material type, and now we need to figure out, and of course the thermal imaging, the emissivity of the different surfaces. Now we need to figure out how to translate that into something the homeowner can use, or something that a utility or partner or someone else could use. And so we do a few different things. We start with various data that we've collected, that I've been discussing so far. We take in GIS data, which helps with the building recognition, but it also helps with some of the calculations. So from GIS building footprints, for example, we can get rough estimates of the wall square footage area or the attic square footage area, which informs some of the savings calculations. We also pull in property records for homes. So for pretty much every residential home in the country, there's publicly accessible county tax assessment records that include the year the home was built, its square footage, number of bedrooms, number of bathrooms, the exterior material type, sometimes the space heating fuel, whether they have a pool, various things about your home are in the public domain. And so we pull in all that for all of our programs, which provides another useful data stream. And so we do building detection, where's the building component detection, as I was discussing earlier. And then we have a building and remediation model. So we're looking at the 3 different types of heat transfer: conductive, convective, and radiative. We also pull in various climate data, hourly weather, going back a couple years. We pull in billing data if our utility partner gives it to us. We don't need it, but we strongly prefer it, either monthly data or smart meter data. And then we use that to run through a sort of a simple financial model and a recommendation model to say, based on all these things you know about your home, you should improve your attic insulation, or you should get air sealing done. And you could save, $250 a year on your bills if you do that. It would cost you roughly this much based on where you live. So that's sort of the ultimate output, and that comes to the homeowner in a mailer, along with the thermal image of their home with specific leaks highlighted. And we found that that's a pretty effective marketing approach because people are much more likely to pay attention to something that has an actual image of their home in it. There are, of course, some concerns around privacy and other things, and we want to make sure that we're not freaking people out by sending them an unsolicited picture of their home in the mail. A lot of people realize that their home's on Google Street View, so it's not quite as scary as it would have been 10 years ago. But to avoid some of the scary stuff, we work with utilities. We always send these things on through the utilities brand. They're not some strange company we've never heard of that's spying on them. And also, depending on the utility's comfort level, we've done opt-in programs or opt-out programs where we first send a mailer saying, hey, we're PG&E, we're going to come by and scan our customers' homes to help figure out who can save energy. If you don't want us to scan your home, go to this website, call this number, something along those lines, and we won't do it. In practice, it just means we throw that data out. We're not going to turn the vehicle off as we're driving, but either way, we don't send it home a mailer. If that's strongly preferred, an opt-in program is less ideal because obviously people are lazy and aren't actually looked into things. But we have done opt-out programs in the past for utilities that are a little bit leery about the privacy thing. So as I mentioned, we pull in data about the home from a number of different sources. We have utility data, we have the thermal characteristics, we have parcel level property records, solar radiation data, weather data, rebates and incentives from the utility rate structures, hourly temperatures, and we also do a fair bit of geographic energy use modeling. So in some cases we have limited data about the home, and we can figure out based on where they are, what the likely properties of the home are going to be. I don't want to go into it too much, but we've spent a bit of time looking at how energy use varies across different regions and built a simple model that uses home characteristics of individual homes to try to estimate the heating, cooling, water heating, and appliance energy use. Published a paper on this back in 2010 in Journal of Industrial Ecology if folks are interested. But it's just a simple regression model using REX and RAS data. Yeah?
For the energy models, did you guys rewrite the 3 types of heat transfer energy balances, or were you using Energy Plus or?
So we wrote our own. So the model's gone through a few iterations. In the first version, we were explicitly trying to model conductive, convective, and radiative transfers through the wall for each home. Turns out that the results from that end up being really sensitive to small variations in temperature. So they weren't quite as reliable as we'd like. I'm going to get into a second, or actually I can segue into it right now. So what we're actually doing right now is instead of trying to figure out an absolute value for each home, we're doing more of a relative comparison between homes that were sampled at roughly around the same time. So we'll send the vehicle out in a particular area in the night, say Santa Rosa. We'll scan 10,000 homes. And then what we'll do is we'll look at all of the south-facing brick walls we scanned that night. And we'll use a regression approach that accounts for external temperature, the orientation of the wall, the material type of the wall, all these various factors. And we'll ultimately say, okay, of all the south-facing brick walls we scanned this night, this is the distribution of emissivities. This is the 90th percentile, this is the 80th percentile, this is the 10th percentile. And we'll map those to a prior range of R values that we're assuming for that area. It's not perfect, but given the uncertainties we're working with in data, we feel like a relative approach is going to end up being a bit more reliable.
Can you explain what we're looking at?
Oh, sorry. This is just this is the Chicago area, and this is the average household usage in kilowatt hours for every census tract, based on the home characteristics of all the homes in that census tract. So the square footage, the space heating fuel, the number of rooms, the year it was built, all the various public domain factors.
Okay, so city center use less energy per capita, I guess?
Yeah, per household.
Per household.
Per household, yeah. Mostly because of urban form. If you're in a small apartment, you're generally going to be using less energy, and often a lot less. This is sort of a base layer of pain if we don't have billing data and other things to work with, which we try to in most cases. So here's an example of a few things we might actually see in a thermal image when we're working with it. So you'll often have soffit drafts, the hot area between the top of the wall and the roof. You can't actually see the attic on this home, so we can't show you an example of that, but there are a lot of images where there's a very bright attic, there's a dark attic with some very bright insulation holes that can be fixed. Usually you're going to find one of two things. You're going to either find particular hot spots on a surface, like a wall or an attic, which is an insulation hole, or the overall surface is going to be abnormally bright, which is an indication that the overall surface is poorly insulated. You're going to have window drafts, so you can see the very hot area around the windowsill. You're going to have insulation holes in the walls. You're going to have hot basement walls, though you need to be a little bit careful because the material type of basement walls tends to make it brighter than everything else in images generally. So you really need to do a relative comparison of basement walls in order to get any sense of if they need improved insulation. You can't just go by brightness, which is a little bit of a challenge when you send these to homeowners because they're going to just look at the brightest spot and say, I need to fix that. But we try to generally focus on attic when we can because that's often the best ROI in terms of insulation. Wall has gotten a bit cheaper with some of the blown insulation approaches, but it's still prohibitively expensive for a lot of homes. So unless the home has a really bad wall, we're not going to focus too much on that. And air sealing is relatively cheap and cost effective. So if we can pull out a really distinct area around some of the doors and window frames, we'll often recommend that.
What's your, how many general recommendations do you have in your repository of things homeowners can do?
So the way that our mailers are usually designed is there's a single main recommendation on the front side that usually is one of those three: wall, attic, or air sealing. And then on the back we give some, usually 4 or 5 other recommendations, which are a mix of both envelope-based recommendations, programs that our utility partners want to include, or just general good recommendations like LED lighting, low-flow shower heads, things like that are relatively cost-effective. Your O-Power sort of recommendations.
I believe, not all of the homes will be perfectly insulated, right? So what is the criteria of, you guys recommending someone? Does it depend on the distribution of the neighborhood that you emit, in that particular time? And if something falls in less than 50th percentile, then you would recommend those houses, or what is the criteria then?
So we usually use a couple nights, sort of, depending on the program. We used anywhere from 3 to 7 nights of imaging and all the homes we captured in all of those nights, and then breaking that down by orientation, material type groups, and then looking at the relative percentiles within each of those groups. So you're right that a neighborhood might all be poorly insulated, and so we don't necessarily just want to compare a home to its approximate neighbors because that might not give us what we want. So one thing I mentioned earlier, but wanted to point out because this is a great image, is the materials affect thermal conductivity and also the amount of residual solar heat. So the image on the right here is the top is vinyl siding, the bottom is brick. You'll find that pretty much in all images, all homes that have both, no matter how well or poorly insulated each surface is. So being able to know what material type is what is really important to be able to figure out, the targeted recommendation for that home. So the actual emissivity calculation, as I mentioned before, is a multivariate regression approach, controlling for external temperature, humidity, material type orientation, the camera side of the car, because the cameras themselves can have some drift, and the scan session, because the scan session itself, there could be some drift both between cameras and between days.
Wind?
Wind, yes, wind is also in there.
What about lights?
The wind is a little bit hard because we have a wind sensor on the car, but the car's moving, so we can try to subtract incoming wind, but even then,
Maybe get by having 4 to 7 samples.
yeah. So we've looked a little bit into that. We've also tried pulling wind data from local weather stations, though. Again, the microclimate's going to matter a lot for that sort of thing. So wind is an area of uncertainty. We try, but it's not going to be perfect. And as I mentioned, we mapped the resulting percentiles onto a prior distribution of R values for different areas. That's often itself a tough thing to get a realistic picture of, because there's not good data on the actual R values of installed homes in the country. But we use some general assumptions that things like eQuest and other engineering tools tend to use for different regions. And ultimately what we end up getting is some sort of thing like this, where we look at a specific brick wall, we estimate its R value, we take the hourly weather data from the local weather station, and we figure out the cost across the whole year for heating and cooling, with some broad assumptions about the likely performance of the HVAC system in the building. We know the space heating fuel in most cases. We don't necessarily know if they have, a 95 AFUE gas furnace or a 55% AFUE gas furnace. So that's another area of uncertainty that's hard to reduce. We also can look at multiple surfaces across the same building. So this is a project we did for the military where we scanned some bases, and we looked at the ROI of different features across the building on sort of a McKinsey-style curve. So you have things like window drafts are, relatively high ROI, but small individual savings because a single window is fairly small. Walls, bigger, lower ROIs. So you often see features like that. And then we can also benchmark across multiple buildings on a facility, multiple low-income homes in a city, or low-income low-rise buildings in a city. If there's a lot of similar buildings, you can get a lot out of benchmarking the different features across the portfolio, identifying the outliers and targeting them for remediation. And you can often find some interesting outliers. This is one of my favorite ones. That building might literally be on fire. But you often see some fun ones like that. And as I mentioned earlier, we also use meter data from the homes, and we do a fair bit of stuff with that. So we disaggregate it. We like smart meter data when we can get it. We realize we don't always have smart meter data. So if we have no billing data, we use a statistical model based on building characteristics to disaggregate use into heating, cooling, and other. If we have billing data, if it's monthly, we use empirical models, your classic either a regression model or a shoulder month model to try to pull out cooling use. If we have smart meter data, I'll skip that one, we can do some more fun stuff. And ultimately what we're trying to do with the meter data is two things. One is to better bound the savings estimates we're giving homeowners for specific measures. So if we're saying if you improve your attic insulation, we'll save this much, you'll save this much. If we can estimate roughly how much you're spending on heating a year, we can better calibrate that number to make sure it's not unrealistically low or high. Because just knowing the square footage alone is imperfect, since there's a lot of behavioral differences with thermostat set points, vacation times, things like that, that are going to change home to home. And we also want to identify abnormal seasonal usage. So right now utilities use billing analysis to try to figure out which homes could benefit from HVAC replacement or maintenance programs. But the thing is, if someone has an abnormally high summer use, for example, they may have an inefficient air conditioner. They may also have a leaky home. They may have a very low cooling set point. They may set their thermostat to like 60 degrees every day and have a bunch of cooling because of that. And so you can't really, just based on billing analysis, differentiate those three factors. Now, if you add thermal imaging to the billing analysis, you can remove one of those three. So what we're looking at in some new projects, including one with PG&E right now, is homes that have high seasonal usage but good thermal envelopes. So they're not leaky, but they're using a lot of energy in the summer and winter. And we want to try to target those homes specifically for HVAC replacement or maintenance. And so for that, we've been using, for PG&E, it's AMI data, which is a lot easier to deal with in terms of disaggregation. But we've also done some work with monthly data for other utilities where we're essentially identifying shoulder months, finding finding the most similar homes in terms of usage in those shoulder months, and then comparing the seasonal usage and looking for outliers. there. So homes that are most similar during the shoulder period, trying to find ones that are very different during the heating and cooling period, both for gas and electric. And then finally, what that ends up producing for utilities and homeowners is two things. One is a drive application that's primarily for the utility and for contractors, which is essentially a Google map with all the homes. When we have the home footprints, each individual footprint outlined, they can click on it, they can see the thermal image, both the analytics we produce about it and the actual video drive-by, which is useful for contractors, and the actual mailer, which we send to homeowners, which has an image of their home and some targeted recommendations. So, yeah.
Have you done any analysis on the accuracy of your saving prediction? Like, you know, after they have made the improvement you suggested, how much benefit are they getting?
So we haven't done empirical analysis on homes that have actually implemented measures due to our program. What we have done is compared our values to those that come from a home audit of that individual home. Because in a lot of cases, this serves not as a replacement for a traditional audit, but a lead generator for a traditional audit. So most of the time, you still have someone actually come into the home before the homeowner spends a lot of money on these things. And so we can compare the results that the auditors get to the results that we get. They're generally quite similar. We had Navigant do an evaluation of one of our programs with Pico a while back that was pretty good on that front. We've also done comparisons between the emissivity we're seeing and the build usage of the homes, which is an imperfect proxy but can help evaluate.
The data science on this is really rad, but the hard part with all these programs is do people actually, does it produce action?
Yes.
Have you evaluated that?
So we have. We've seen a very sizable bump in the uptake of rebate and retrofit programs for utilities we've worked with. Their response rate on the mailers has been about 4 times higher than they're used to seeing with their traditional efficiency mailings, in part because people tend to find the image of their home very compelling. And we haven't, interestingly enough, had many privacy complaints. We've got a couple, but they're surprisingly rare, which has been pretty good on that front. We still are a fairly young company. You know, we're only 20 people, and we've only been doing pilots for 2 years now, so it's a little bit hard to get too much data, but the data we have seen so far is pretty encouraging.
And then as a follow-up, are you working entirely with utilities, or do you contract directly with cities who have climate action plans or other things to motivate residents?
We're talking to a few cities. We haven't done any specific projects with them yet. We may be starting one this coming year in Canada. We have worked with individual, or not individual contractors, but companies that sell insulation. So Certainty, for example, if you're familiar with them. We've done a few projects with them. We actually did do one, sorry, I was incorrect. We did do one city project in Cambridge.
Can you talk about your business model a little bit? Obviously, I guess utility would be one. You sell your lead, maybe. Like, how do you make money?
So selling data to utilities is part of our business, but it's not one we want to focus on, in part because just selling data is pretty low margins. We like to run efficiency programs for our utility partners, often ones where the RPA is tied to the performance of the program. So sort of like an O-Power type approach would be. You know, we can usually get a larger chunk of efficiency budgets if we're actually program implementers rather than just data providers. Though we have done a few other projects with, for example, the military, where we're just paid to scan a base and provide a report along with all the imaging. And we're doing projects in New York right now on scanning grid infrastructure, so identifying where all the utility poles are, figuring out if transformers are overheating. We've also talked to a couple of companies in the oil and gas sector about using the drive imaging in some of the refineries to figure out if there's any overheating components that might be of interest. We've looked a little bit into detecting fugitive methane leakage, but it's hard for the vehicles to get around well pads and things like that. Thermal cameras mounted on drones might be a little bit better approach for that, and I know there's some folks down at Stanford working on that.
And you don't sell any leads to contractors?
Not directly. There's just too many contractors, they're too small. It doesn't scale that well. Utilities are much easier and high value. I mean, we'd certainly be open to it, but if we just haven't been able to figure out ways to get the transaction costs down far enough for that to work.
Yeah, you're getting the insulation manufacturer.
Yeah, the insulation manufacturers.
Right, it's a different, you mentioned 4 times the typical response rate.
Mm-hmm.
I know that varies widely between different utilities, can you actually share the absolute number?
I'm trying to remember if I know it off the top of my head. I think it was like a 4% response to the program that Navigate was evaluating. So 4% of the people who got mailers ended up calling the utility to inquire further about the
typical
programs.
direct mail is about 1%,
Yeah.
so that would.
So is that only 20% of the people get the mailers, the worst 20% get the mailers, and 4% of those are
Correct.
responding?
So it's still narrowing it to a pretty narrow funnel at the end of the day. But, a lot of utilities have pretty aggressive targets to meet for their weatherization programs, and they're doing a pretty bad job of meeting them right now.
And you're
So-
picking the top 2 or 3% that are consuming 40% of the excess energy.
Not quite that bad, but yeah.
So are customers, when they receive this, are they given a comparison of where they stand with their neighbors as sort of an added incentive?
So for some programs, we have done a normative comparison. You know, here's like in terms of we actually the one program I liked, we did it based on hours window open equivalent. We didn't call it that. It was essentially your home leaks enough that it's like leaving your window open for 80 hours a year. We had like your home, the average home, and the most efficient home in your neighborhood all on that chart.
Yeah.
So we have done that. It's gotten some pretty good response. We definitely like normative comparisons. It's a little bit harder when you're talking about emissivity to compare it than if you're just looking at bills, but we definitely looked into it.
Does the utility give you some like heads up, like go to this area, there's some like real bad actors in this area, or they're just like, why don't you just drive and tell us what you see?
Mostly the latter. We've actually done most of the filtering beforehand. So often when we're looking at an area, we'll buy property records and demographic data for that region and try to figure out, you know, these are the areas that have the older homes. You know, we don't want to focus on a neighborhood development that, you know, all the homes were built 5 years ago because chances are they're going to be decent in terms of envelope. You never know. But at least in somewhere like California where there's strict building codes, you know, you only want to focus on old homes. But we do that mostly ourselves. In a couple of cases, we've gotten utilities to hand over all of their customers' billing data to us beforehand, but that's a rarity. We usually only can get billing data from specific homes after we've scanned them. Can't use that as a filter beforehand.
You mentioned having to manually build a training set with like a couple 100,000 homes. When you want to switch to deploying this like in a refinery or for utility poles, do you have to go through that process again of manually building massive training sets? Is that a
So for utility poles, we did. Again, it's relatively cheap because you can mechanical turk that pretty easily these days. Or similar type programs. For something like a refinery or a military base, which is more of a one-off, it's more likely we're just going to manually do the whole thing rather than trying to rely as much on image recognition, and just have, you know, people go in and manually identify specific components and draw polygons around them. Just because we're not doing enough refineries that it's worth trying to automate that. And something like a refinery is going to have a lot more heterogeneity between components. You know, residential homes are relatively homogeneous. Refineries, not so much.
Thought about doing some of the normalization, all that fancy normalization you're doing behind the scenes. Have you thought about putting that back into the imagery? To present an image of, you know, your windows relative to the average, etc.
It's an interesting idea. Essentially, instead of just showing the thermal image, have like color coding of components based on their relative performance. We haven't looked at that specifically, but it's not a bad idea. It's just we only have real estate for one image of the home, so we'd have to do some testing to see if people prefer just the thermal image, which is fairly consistent to our image with the image of the home.
As you said, it's deceptive in some ways.
It is deceptive in some ways, yeah. And even then, some homes with like really bright spots aren't necessarily the worst insulated homes. So it's yeah.
What parts of the country have you guys done pilots in? And then, secondly, what's the primary activity between April and October?
So April and October is every year we upgrade the vehicle. So we take apart the whole system, we add in new components, we test new things, we rebuild it, we add other vehicles. We're also, you know, there's an endless amount of work on computer vision, on energy analytics, on other things that keeps us busy during the summer. We just don't have the drive teams going around. In terms of projects, we worked with a number of utilities in the Northeast, because that's kind of our starting area. We've worked in the Midwest, Chicago area. We've worked in the South, North and South Carolina, and we've worked in California so far. But we're still, as I said, a fairly small new company. And utilities are notoriously slow and risk averse, so it's been a hard slog to get them to do these pilots.
I've got a question about San Francisco.
Mm-hmm.
Do you think there would be like a very big difference between neighborhoods due to San Francisco's erratic climate?
I don't think in terms of the image quality
No,
or the insulation.
In terms of like energy usage.
There's probably some differences in energy usage. I mean, in general, homes in San Francisco are terribly insulated and very leaky, but it doesn't matter because it's warm all year round and not hot. I mean, the West Coast has the benefit of having the least combined heating and cooling degree days of anywhere in the country. So if you're going to focus on weatherization and insulation programs, this is a terrible place to do it because even though the homes are poorly insulated, you're still not going to save that much. I mean, it's still worth doing it here, don't get me wrong, but it's not the low-hanging fruit. Yeah.
Can you get any meaningful information for commercial building envelopes, considering that air conditioning is the main user of energy in the commercial sector?
So commercial can be a little bit harder, especially if their commercial buildings in more temperate zones that are heated at night. So if you're looking in, say, the Northeast or the Midwest, most commercial buildings are heated at night, even if they're closed, to keep pipes from freezing, things like that. And then we can see the envelope. And it turns out that if the building is leaky in the winter, it's also leaky in the summer. The same insulation gaps, air leakage, and whatnot is going to affect cooling and heating relatively equally. It's a little bit harder for commercial if we're looking in more temperate areas because often there's no heat on at night, so we can't really see anything. But we have looked at commercial buildings before for a few different projects. But you're right, that it is a bit more challenging because they don't heat as much.
And do you have a plan? Are you planning on doing commercial too?
We're definitely planning on doing commercial too, and industrial if folks are interested. It hasn't been our main focus to date, in part because there's a bigger efficiency market for weatherization on the residential side, but we're certainly open to it and our technology can handle it. 2 more questions.
So it's interesting to see how many actually states you've worked in. You're way farther ahead than I would have thought in this stage at all. Kudos. But are there, in the way you contract, in the way you get contracted to do these energy, are you able to, as you map out eventually the whole country, are you able to use the network effect of all that data, or is it all private for the utility?
It depends on the project. So the images we're collecting are ours. They don't belong to the utility framework projects. Any data they give us is obviously theirs. There might have been a few projects where we had to sign specific things, but I can't get into the details of that. But generally speaking, the imaging is ours and we can use it for other things. It doesn't necessarily reach that well, so you wouldn't want to use like 5-year-old imaging. Well, it wouldn't be awful, but you'd probably want to rescan with some regularity. And we have been talking to a couple folks about the idea of scanning all the homes in an entire state, which really isn't that much work if we're doing 10,000 homes a night. It's a winter, but it's definitely doable. So we'd love to do that in the future. It's just getting the funding. And I think you had your hand up first.
Do you know if there's satellite data of that quality available that you could use for exploring?
I know there's been some folks who have looked at using satellite radiometer data for roofs. We haven't looked in that much detail. For most things, I think the resolution is a little bit too low, but to be honest, I haven't looked at it too much. I've looked at satellite infrared data for some climate things, but not for this.
Excellent.
Okay.
Thanks very much, Zeke. Great.